Hello, everybody. My name is Milan Stehlik, and I'm the corresponding author of this paper, where we have been studying the COVID-19 Outbreaks Predictions, and we have been concentrating on various issues of importance like the stability of these models, parameter sensitivity, and precision. In the coronavirus pandemics, especially this year, we have seen certain problems with getting a precision on the modeling of the COVID outbreak, like modeling of the starting point of the outbreak and the form of the outbreak, which have been causing the important problems to the policies. And this also motivated our paper how to avoid these problems of the models and how to address the correct features of the models and choose the proper models and calibrate the models so that we are not having a problem with the precision. So the main motivation is that we have been studying the exponential growth in outbreaks, and we formulated the importance of proper recognition of exponential growth. In several countries happened that the start of the exponential growth was misspecified with a tremendous effects in a negative sense for the economy and policymakers. So the most simple model, which is parsimonic, and also it is very generic in the same of in the sense of the epidemics growth modeling, is exponential curve, which is just the two-parametric exponential model, and which is justified from the microbiological and virological point of view. And this is also explained in our paper why this kind of model is a reasonable model for outbreak. And many sophisticated models like SA, NARAN, and others do not address these virological aspects properly, since they simply receive a very high vulnerability with many parameters and exploding variances if these issues are not put into the control. So motivation of this kind of exponential growth can be the data from Iowa, USA. We have observed this in the spring. And then Hubei, we can see the outbreak here, and the New York, the outbreak is whole part of the diagram here. And the similar thing have been visible in Santiago de Chile. So we also developed the follow-up methodology, Redux, which is based already on the results from this paper, and which minimizes the problems of fitting of exponential model. Fitting of the simple nonlinear exponential model is far from to be easy. Here we illustrate the sensitivities of the parameters and variability of the parameters when we are putting a different periods and numbers of infected in the Iowa setup. And you can see that when we are computing the starting values of parameter B, which is necessary for nonlinear optimization procedures, then the instability is very high. So the other things we have been discussing is an important topic of the sensitivity of parameters of exponential growth. So if imagine the simplest exponential growth model, which is on the form like a times exponent to the b times t, where the time is the time, a is the nominal value. And here we illustrate with a 122 nominal number of infected persons in time 0, which is equal to 0. And we illustrate how sensitive is the parameter of the growth b of the exponential growth b, which is in the exponent multiplying the time. And with a nominal start of 0.156 and 0.12, we see the big difference. Albeit the percentual change of the B parameter is only 30%. In the 2 weeks, approximately the percentual change of number of infected is 65.5% different. And we see that there's a real difference here on the number of infected. And this is happening with many of the models, so that what we can see, many models are keeping close to the real number of infected only during the very short periods. So the sensitivity of the parameters is playing a very, very high role in the modeling of the outbreak. So nominal parameter has just a linear change. So when parameter is changed by 1%, that the state change in number of infected is only 1%. That's fine. The problem is with the growing parameter in the exponent b, which can be changed by p%, and the change will be increasing with the time we are observing the exponential COVID-19 growth outbreak, and also with a nominal value of the b parameter. So the speeder is the growth, the higher change will happen in the number of infected. So we discuss in the paper also important COVID-19 data quality issues which we cannot overcome easily, and these are discretizations of the continuous models like a SEER or a SAIR, which can converge to different equilibrium. Like what can, for instance, happen in a practical sense is that mortality will be underestimated severely. And this will need a very careful calibration of the parameters, and just ad hoc fitting with uniform priors will not make the job. This issue has been already observed by measles and have been studied since 80s or 70s last century on other diseases. But it is a very new topic in COVID-19 with its own specificity. So a non-uniqueness of the solution of the model and prediction can happen. So we are observing a predictive model, and it can bifurcate to the 2 or more branches after given time. And that is also giving limitations to the models, which will bifurcate for watching towards the future. And another one very important thing is identifiability of the parameters. When we don't have the identifiable parameters, which can easily happen with continuous models, then it's very hard in the discrete models to get identifiability, and then we can get multi-valued outputs, which not necessarily will be the things we want. So COVID-19 data quality issues we realize is a very important topic, and we also organize a special issue by Taylor and Francis Just Journal of Applied Statistics journal, which is related to these topics. Another one very important problem is to have a good data on the hand. So data are not perfect. Our data on the COVID-19 typically can be affected by delays, by the different governmental procedures, by the different type of recording and availability. But they can also suffer from mistakes and stochastic perturbations. So even the number of infected people, like example here, comes from control testing, not from the random sample. And this we also try to integrate with the success in our method Redux, which was follow-up of this paper, which is now under consideration for the journal. So parameters, like if I can take a SIR model, might often depend on time and other space variables. And finally, all real processes which are included in COVID-19 can suffer from delays. So this can bring us a problem of the more dynamical thing that we already have, which delayed discrete systems are not easy to solve. So in a summary, in our paper, we formulated in a practical sense the ill-posedness of inverse problems of estimation and prediction of COVID-19 outbreaks from statistical and mathematical perspectives. And we justified an exponential form of COVID-19 outbreak from microbiological, virological, and a stochastical point of view. We compared sensitivity parameters for several models, like a simple but parsimonic exponential model and an SIR model. And we use empirical data for illustration from Iowa State in USA, Hubei province in China, New York State in USA, and Chile. Thank you for your attention.